claim about a population proportion. We did some examples from the homework. By now, you guys should be pretty familiar with this notation, right? Let me know if you see anything that you want me to explain a little more. But I think you guys are going to understand what's going on. We're going after P, right? The population proportion. What I have is P hat. Q is 1 minus P. We know that. Requirements for testing claims. Okay, now this, yeah, I haven't said boo about yet. So let's go through this. I'll get my red pen out here. Okay. Hey, guys, isn't this just about always a requirement for almost everything we're doing? Simple random sample? Yeah. The conditions for a binomial distribution? Wait a minute, that was on the last exam. What the heck was the binomial distribution? This was when you were counting the number of, do you remember what I called them? I called them successes, right? What the heck are successes? I don't know. You either have success or you have what? Failure. Hey, I want to go back to the example we just saw on the board about Italian food. Maybe success would be they like Italian the best. That'd be success for places like Maggiano's, right? And then failure would be, well, they like something else the best, right? So do you see how what I have here on the board is basically a binomial problem? How many trials were there for success or failure in the example on the board? Problem 27 up there from the last section. It's either yes or no. I had 314 people say yes. That's their favorite. Out of how many? Yeah, so we have N is 1,122. So this again is, I'm doing problem 27 from 8-2 because that was on the homework. What's P? Well, P ended up being, we had to compute it, right? Okay, so yeah, that's the claim was that P is 0.25, right? That was my H naught. That's the null hypothesis. And then Q was 0.75. So you really do have the same kind of thing that you have for a binomial distribution. Okay? Now, they list these other little requirements. I've not been a big stickler about this. This is a way of testing, will your binomial distribution look like a normal distribution? See how it says the binomial distribution of sample proportions can be approximated by a normal with mu equal this and sigma equal that. I have to warn you, we skipped this. This is all section 6-7. Nope. So I kind of want to just say one time this. If you have a binomial distribution, and if you meet condition 3, here it is, you can approximate it by a normal distribution. In other words, we don't have to go back to do the chapter 5 stuff. We can still just do a bell curve as long as it meets certain conditions. Hey, by the way, notice, if n is really big, right, won't these things be true? I guess unless p was really, really small. But it's not. It's 0.25, so we're okay. All right. Here's our test statistic. Craig already put this on the board for us in the example we had. Just use the standard normal distribution. So use normal CDF, right? If you want to get the p-value, use normal CDF of whatever z equals. Right? Well, z to, to something. Like 10. Or sometimes we do something like negative 10 to z, right? It's something like that. Critical values, if you're going to go that route, that's when we use the inverse norm of something. That's when we're going backwards. Caution. Now, we said this yesterday. Don't confuse big P, the probability of getting a test at least as extreme, with the little proportion value P. Just don't confuse those. Here's another example. May as well do this before break, huh? It says the text refers to a study in which 57 out of 104 pregnant women correctly guessed the sex of their babies. Look at this claim. They claim they're better. They claim, hey, if I'm the mom, I have a better than 50% chance of guessing the sex of the baby. Now, why? Well, because somehow they're in tune. Right? How many have heard people claim that they can guess the sex of the baby? You know who I found are very good at it? Or so they claim? Grandmothers, yeah. Oh, yeah, Noah just had a baby recently, new one recently, and I bet people have... She was right. Does that prove it? Well, okay, so just without doing any analysis, we would think it's a 50-50 shot. The claim here is that mothers will have a success rate different from the 50%, right? Well, greater than 50%, right? And here they say, let's use a 0.05 alpha. Okay, and they want us to use the p-value method. All right, so let's go through how this works just very quickly. I'm not going to do everything. First of all, they check in the book that the requirements are satisfied for us to do what we're going to do here, this finding the proportion with the z-value, finding p. You have a fixed number of trials. There's two categories. Guess correctly would be what? Success or not guessing correctly. Has to be either one or the other if you're going to test a proportion. You guys see that? They compute NP and NQ and check that they're both bigger than 5. Again, that's the section we skipped, but they're checking to see that the requirements are all set. This is all in the book. Step 1. The original claim is that the success rate is no different from 50%. Right? Because they got 57 out of, 104, right? So they got, double check that. It was 57, yeah. What does that equal? 0.53? Here, let me get it. 57 divided by 104. So they got 0.548, okay. So basically, we're going to see, hey, does that mean that they're better than 50%? I mean, in my sample, there were more, but does that mean that in the population, there's more? Well, let's find out. The original claim is someone says, hey, wait a minute. We think, this is what some of you guys up front were saying. You were saying, no, they have a 50-50 shot. So that's P equals 50. The opposite of that original claim that we're going to test would be P does not equal 50%. Now, P does not equal 50% has no equality in it, so that's going to be H1. Remember, H1 is what we wish to verify, right? If you're trying to support a claim, or if you're trying to support a claim with your study, you have to make that H1. Because what's the only thing you can do with H naught? Reject or fail to reject, right? So let me go through this again. The people doing this study want to say that, hey, P is 50%. Well, if you want to say that P equals 50%, is that good? No, because equals is H naught. So that's why they do step 2. They say, wait a minute, let's do the opposite of that. P does not equal 50, and we'll call this H1. That's what I'm going to try and verify. Yeah. This stuff here, don't worry too much about it. These are requirements. In order to do hypothesis testing on the proportion, there's certain requirements you have to satisfy. I mean, the other thing you need is a simple random sample. They didn't say that, but I'm not too worried. I just want you to know there are requirements. If you want to read more about what the requirements are, it's in the book, and it's also section 6.7. Okay? But it won't be tested on, so I want to stay away. Jim? That's the original claim. We want to see if we can support that. Yeah. Well, let's just say that whatever you're... Okay. I understand. Let's watch what happens. Okay? I can't explain it without showing to you. Okay, then I'll shut up. Let's watch it. So, step 4. We know the significance level is alpha equals 0.5. P-hat couldn't come in, but here we go. Step 5. The sample involves proportion, so the relevant statistic is the sample proportion, right? If you're going after P, then the statistic you want to use is P-hat. The formula for P-hat? Well, that was the 57 out of 104. So they calculated a z-value, right? This is the same formula that Craig used. We're not going to go through it all. It's all in the book. It's all in the book. But they got z equals 0.98. Let me ask this. What are we going to do next? Yeah. We're going to what? Well, which one? Yeah. We want to do normal CDF because on a picture, what is this a picture of now? Here's the curve. Here's the mean, mu is 0, let's say, because this is a z-value, right? So for the z-value, mu is 0 and sigma is 1. Okay, so here, right here, is 0.98. Hey, by the way, I could tell already. Look at what I'm about to find. I'm about to find the p-value. What do you think? Is P going to be pretty big? I can tell from the picture. If Z is 0.98, and if one standard deviation, I said, is about halfway down the hill, it's going to be a big p-value. We'll see that shortly. Two-tailed test. Oh, wait a minute. Why is it a two-tailed test? Because the claim was, let's go back to it, the claim was P does not equal 0.5. That's a two-tailed test, right? The original claim was P equals 0.5, right? We said we can't support that because it's an equals. So instead we do the opposite. P does not equal 0.5. We're going to try and support that. So H naught then becomes P equals 0.5, the null hypothesis. We go through this and we say, okay, we have a two-tailed test. So what we're going to do is we're going to do, here, let's do it this way. If I did normal CDF of 0.98 comma, say 10, I would get 0.1635. Okay, that's what I would get. That's what they did with the table instead. Now, why do they double it? Two-tailed test. So there's your p-value, 0.3270. Or 0.3268, something like that. Yeah. Yeah, if it's a two, well, it depends what you computed, but on the picture, see what I computed? When I say normal CDF of 0.98 to 10, what did I just figure out? I figured out this area, right? See that, Jesse? So that's why I doubled it, because it's two-tailed. I only did one tail on my calculator. And they say, all right, that's greater than the significance level, that's a typo, of 0.05. So fail to reject the null hypothesis. I'll have to fix that. So, no, yeah, so the significance level is not 50%. The significance level is 0.05. So fail to reject the null hypothesis. Okay, are we done? No, because I just gave you a statistical jargon. I said fail to reject the null hypothesis. Now we have to make the correct conclusion. Okay, so kind of like I did on the board. When I said fail to reject, we say there is not sufficient evidence. There is not sufficient evidence to warrant rejection of the claim that women who guess the sex of their babies have a success rate equal to 50%. Again, let's write down what we had. What was H0? P equals what? And H1 was P does not equal 0.5. And what I'm saying is my study didn't give me enough evidence to reject that P equals 0.5. Yeah, guys, it's nice that 54% of the women guessed right, but that doesn't mean that it's not a 50% chance of getting it right. We don't have enough evidence yet. Now, what if we had done a study and 90% of the women in our sample guessed their sex correctly? Well, that would change your p-value, wouldn't it? And then at the end, you might be able to say something positive about that claim H1. You might say, hey, we reject the claim that it's 50%. Follow that? Okay, we got 11 o'clock. Let's take our break. Testing a claim about a population mean. Okay? So what's going on here? Well, let me do this. Let me give you the key concept. Remember this student T distribution? Do you guys remember that? That was a different distribution that we talked about. We used this if you're trying to find what? Finding mu, right? If you're trying to find the population mean, we had to use a different distribution. Here's some notation. We still have n as the sample size. That's not new. X bar is the sample mean. Oh, here's one. Do you know what this means right here? Mu x bar? What the heck does that say? Well, what does mu mean? Mean of the sample means. There you go. Population mean of all sample means from samples of size n. Okay, now, this is getting a little confusing. I want to go back to the Social Security number example. Remember on the board, we had the numbers 0 through 9 in a little dot plot, right? And we put dots. And those dots ended up being pretty uniform. Remember that? And then what do we put over on the right side of the board when we had the numbers 0 to 9? Those were what I would call sample means. How big were the samples we were taking the mean of? How many digits were you taking the average of when you did that? 4, right? And you were computing X bar. When we did those X bars and we put them on the right-hand side, what did the picture look like? Well, didn't it look kind of like a bell curve? And we said that the central limit theorem says over time it's going to look like a bell curve, right? You follow me? Okay. So, you might say, what's the population mean if you took every possible sample of size 4? Well, that would be this. Why was it 4 for us? Because we did the last 4 digits of your Social Security number. That's the 4 that we added. I mean, that's an example. You're right. N could be whatever you want. Okay, guys. We're going to have a list of requirements again. Seems like we've had this a lot lately, right? What are the requirements for if you want to test claims about a population mean? By the way, let's compare these to the requirements for the proportion. Okay? Let's compare them. We'll see if they're the same or different. How about that first one? Do you need that for a population proportion? Yep. You always need a simple random sample for the stuff we're doing. The value of the population standard deviation sigma is not known. Now, I got this slide from the book. They're just doing this because remember what they did in the last section? They pretended you knew the standard deviation. You're not going to know the population standard deviation. So I'm not worried about 2. Here's 3. Either of both of these conditions is satisfied. Either we have the population is normally distributed, or n greater than 30. Why is it okay just to have n greater than 30? Craig?
Law of large numbers states that well, over time it'll make a bell curve, which is normal distribution.
That's just about right. The law of large numbers actually you can use to prove what's called the central limit theorem. And the central limit theorem says we are close enough to normal. We are close to normal. We are close to bell curve. I've been trying to tell my wife the whole time I'm close to normal. She don't believe me. But, you know, if n's greater than 30, we're close to normal. Okay. Whoa! What the heck is this? Oh, wait a minute. No. Don't panic. Yeah, we always get these formulas. Before we panic, haven't we seen these 2 words together before? We just had it. We just had it, but it wasn't t equals. What did it say last time? Z equals. Craig, is it still on the board? There it is. Remember this? P hat minus P over square root of P Q over N, right? That was what you used for proportions. If you're trying to find P, you need to use this formula which had P hat in it. You guys remember that? Raise your hand if you remember what I'm talking about. Okay, now we're going to try and find mu, the mean, right? If we want to find mu, I told you you're going to have to use the t distribution. And here's the formula that we're going to use for our new test statistic, t. T equals x bar minus mu x bar over s squared of n. Okay. And basically we're going to do the same thing. After you have the test statistic, guess what I'm going to compute next? The p-value. And if the p is low, what's going to happen? The null must go. So this section is not horrendously different. It's almost exactly the same thing. I guess the biggest difference is you're using a different distribution, and you also are using a different what? Test statistic. Yes?
I thought the test statistic was Z.
Well, it was for proportions.
Okay.
So you really have to know, what are we trying to find? If you want to test a claim about P, then you use this. But if you want to test a claim about mu, the mean, you have to use this, right? That's why this is a whole other section. In these problems, you're going to be testing claims about the mean. Do you guys understand the difference? The great thing is, since we're doing both sections for homework for Tuesday, you'll practice both. Okay. Now, let's see how this goes. Yep, p-values, we know what those are, right? And critical values are still going to come into play. I mean, again, this is the traditional method where you draw pictures. And this is where you compute, then compare to alpha. So the traditional method, again, has pictures. And I'll, in time show you both of those approaches. Okay. But it's the same thing we were doing before. Found in table A3, really? Okay. Oh, yeah, that's why this is here, because there's something you might remember that's a slight complication. When you use the t-distribution, do you remember how the t-distribution had lots of rows in the table? And you had to look up, what's df stand for? Degrees of freedom. It was like the number of free variables. And I didn't get into it too much. We just knew that it equaled n minus 1. Okay? Kind of tells you which row of the t-distribution you're going to want to use. Holy mackerel! That's too much for a slide. Yeah, let's skip that. Okay. How do you choose? Wait a minute. It did say important, didn't it? That's okay. We'll get to it. How do you choose? Well, it's too much. It's on page. Thank you. It's on page 433. Okay. How do you choose whether to use normal or student T? All right. I'm going to do this. Put a big X through this. Why am I putting a big X through this? Because I'm going to tell you, let's use student T. Let's just use student T. See, they say do it when sigma is not known, right? Okay. Let's move on. Example. Boom! Okay, this example's in your book. Let's pause while you find it. Use these results to test the claim. We want to test what claim? Test the claim that men have a mean weight greater than 166.3 pounds. Oh, I see. Mu greater than 166.3 pounds. See, here's the deal. National Transportation and Safety Board said, hey, as long as the mean weight is 166.3 pounds, we're okay. But now we've been noticing data. There's been some deaths. We don't want those to happen. Maybe it's because men are bigger than they used to be. I mean, that's actually a known fact if you go back hundreds of years, thousands of years, right? So it makes sense that over time you might want to update what you allow for capacities for boats or for any object, right? I mean, things change over time in terms of how strong you have to make something. Okay, so that's the claim we want to test. Mu bigger than 166.3. And they say, let's use alpha as 0.05 and the traditional method. All right, let's walk through it. So what happens? Always check that your requirements are satisfied. Well, we have a simple random sample. Population standard deviation not known. Sample size is 40. That's good. Right? So check. We're all set for requirements. Step 1. I already wrote that on the previous slide. Remember that? Mu is bigger. That's the claim we want to test. By the way, if that's the claim we want to test, could that be H1? Could that be H1? Yeah, because there's no equals there, right? So it could be. The alternative to that claim is mu is less than or equal to 166.3. Okay? So what am I going to use as H0? Here it is. Mu equals 166.3. And we'll use as H1 mu bigger than 166.3. Which means what kind of tailed test are we going to have in this problem? Right-tailed test. You guys are getting this. It's kind of fun to watch. Example. Step 4. They just put this here because they didn't know how to make it disappear. I told you, this is from the book. So the significance level is alpha is 5%. The claim is about the population mean, so the relevant statistic is the sample mean. Did they give you the sample mean, or did you have to compute it? Oh, they gave it to me, right? That's X bar. They gave me that. Notice that's what's going to go right here. Notice what's going here. Mu of X bar, the mean of the sample means. See that? So yeah, that's what they claimed that the mean was. Now let's see if this makes sense to you. If mu is 166.3, that will also be mu X bar. Because this is the mean of all possible samples. So that's what's going to go here. Is everything else clear as far as where they got it from? What's S? Uh-oh. What's S? Do you guys know? No, I mean, what does it stand for? Okay, standard deviation of the sample. Well, I guess we are almost on time. What is N? That's the sample size. 40. Let me just try and wrap this up real quick. Holy mackerel. Degrees of freedom is 39. Because why? Well, that's 40 minus 1. And so when you look in the back of the book at your t distribution, you have to look up one tail, 0.05. And I'm looking at row 39. And sure enough, I get 1.685. So there's the picture. 1.685 is past the critical region. Okay? And so you'd want to reject in this case. I guess since I'm out of time, I will let you go. We can, yeah, I can go back to slide and leave it there. And have a great weekend. Stop by office hours if you need help. Otherwise, I'll see you Tuesday.
How often do you check your email if we need help
Pretty
over
often.
the weekend?
Yeah.
Okay.
I mean,
A couple questions in there.
yeah, go ahead and ask me. Come on. And the worst going to happen, it'll sit in my inbox, but usually I try and get back. I don't know. How long does it take me, Craig?
How long?
2 hours maybe,
Oh, really awesome.
which is pretty short.
So you say we failed to reject?
So it was in the critical region. That's what I saw. Let's see. Oh, no, it's not. You're right, it's not. Yes, it's not. So we would fail to reject. Yeah. This is in the book.
And how do we get that t-value again?